So, hi everyone. Just a second. Okay. So first, a few announcements. Uh, sorry. As it was suggested to me, in the future, I'll try to send the study guides a bit more in advance. The one for this week was sent only a single day beforehand. For next week, I'll try to send it a bit earlier. I'm aiming probably for tonight, otherwise tomorrow. So we'll have it a few more days before class if you want to do some reading before coming here. Also, I'll go a bit further than I had first planned this week. I first planned for today to be mostly qualitative introduction to diffraction, but I figured in order to have a much better experience next Monday, we better to go a bit further and introduce the equation for diffraction by itself before uh, before moving on to combine it with interaction. So maybe if some of you can communicate with Jan if she has some question at least for today's class, if you could just write them for her if you can. We'll have to check this out some other time. Just for today, if you don't mind just writing for her whenever she has a question, I would really appreciate it. So yeah, since this week we'll go a bit further than I had first planned. I released on Lea an add-on to the first study guide I had published. So an extra section about four more exercises, uh, three more examples, I think. So a little bit more, not that much, but still a little bit. That would have been covered normally next week, but I think it's better to do it this week instead. I also have a short remark to do on yesterday's class, something I forgot to mention. So just to go back to what we had previously said, yesterday we started our study of interference, meaning we started looking at light not from the point of view of simply rays, but as a traveling wave, which could, if coming from multiple sources, interfere to create some bright parts and some dark parts. The bright parts corresponded to constructive interference, while the dark part corresponded to destructive interference in that case. We developed some equations to find the position of these fringes, the bright and dark, first in a general case, and next in the small angle approximation, which I introduced as being less than 10 degrees. However, something important must be said about this. You cannot, in general, solve a problem, take out your protractor, and measure an imaginary angle. So we'll need some kind of hint to know whether or not we can use the small angle approximation. Sometimes you'll be able to compute the angle on your own. Some other times it might not be possible. In that case, whenever we say that the angle is small, the angle was measured compared to the center of the screen. So it means if the angle is small, that we're not going too far away from the center of the screen. In terms of our equations, that means if the index m of the bright and dark fringes we are looking at is not too great. If we're looking at a fringe for whose order is 0, 1, 2, 3, chances are it's pretty close to the center. However, if you're looking at the 50th or 300th fringe, it's probably a bit further away from the center. So the small angle approximation might not be such a good idea for this case. So you can gauge it also with the value of m. If you're not sure, the general case always work if you are willing to put in one extra line of calculations. And I believe that was what I had to go back on your end before we move on to diffraction. would you have something you would like us to go over once more? Otherwise, we'll start working on diffraction, which starts our study of chapter 36. Diffraction, uh, to study it, we'll have to study how waves behave whenever they encounter obstacles, some kind of object, or some kind of aperture, such as a slit in an object. How does the wave behave compared to this kind of object? Well, the behavior depends on the wavelength of the wave you are studying. Lucky for us, right now we have access to two very different waves: sound, since I'm talking, and light, since you can see me through the camera. These two kind of waves are very different from each other. Light, well, first, their nature is not the same at all. Light is an electromagnetic wave which does not need any kind of medium to travel, whereas sound is a mechanical wave, so requires some kind of material, in this case, air, so it can propagate with the particles colliding with each other for the wave to continue propagating forward. Their wavelength is also very, very different. In the visible spectrum, light has a wavelength between about 450 nanometers for blue and violet, and around 650 for red light. So of the order of about 500 nanometers. A nanometers is 10 to the power minus 9 meters, so quite small. Whereas the sound emitted by a human voice has a wavelength of the order of 1 meter, can range 50 centimeters, 1 meter, 2 meters. Still, even with a variation of factor 2 or 4, it is a much larger wavelength than light. And this will affect how it interacts with obstacles, such as my trustworthy pad here, which I'll use as an obstacle. So if I put it in front of my face, so that it is between myself and the camera, you cannot see me anymore, or at least my face, but you can still hear me talking. That is because light cannot bend around the pad to reach the camera, but sound can, due to its very different wavelength. In the setup I'm right now, if you're looking around me, you should have a very valid objection to what I just said. I'm surrounded by walls on all four sides. I have a ceiling above me, a floor below me. So there are plenty of surfaces on which sound can just reflect and then go towards the camera without ever needing to bend around an obstacle. So to do the demonstration of why this is not really something that we have, that is not, let me start over, just to demonstrate why this is not that important, why this behavior still occurs even without reflection. I'll have to ask the person I trust the most with this, uh, my very own past self. Past self, how am I doing?
Oh, I'm your. Everything's fine. Yep.
So my apologies to those watching. Since the signal literally has to travel for a very long time, there might be some delays in the conversation, so please bear with me.
So, what can I do for you, future self?
Well, I need you to help me with an experiment. I'd like to illustrate the difference in behavior between sound and light, but without having to deal with reflection. Could you help me with
Sure
this?
thing, but only if you agree to do my tax report.
Okay, but it's the last time. Next time, please do it earlier.
Sure it is. Alright, so light and sound. If you look around me, you'll see this place is not stuck between four walls. It is a lot more open than what my future self is working with. There are a few trees, some houses nearby, but still we're not stuck between four walls. So reflection should not have as much of an impact as it did in the other case. So what I'll do is I'll place an obstacle between the camera and myself. So I just place this cardboard piece. Now you cannot see me anymore because light cannot pass through or around this cardboard piece. However, you can still hear me. The key is because the light wave and the sound wave do not interact with this obstacle in the same way. They interact in a different way due to the difference in the wavelengths. The sound wave has a much larger wavelength than the light wave, which makes it interact in a different way. Is that right? Is that right, the future self?
It is very much so. So, thank you for helping me today, and you'll see me later. Bye bye.
Bye bye.
All right. So, as demonstrated here, even without having reflection to make the sound go towards the camera, sound could still reach it because it could bend around it. To illustrate this, I prepared a few diagrams. First, the situation we dealt with. This corresponds to the obstacle. In our case, it was the pad. Thank you. So the pad I used in the experiment, represented here by this rectangle. In the top case, when studying light, and at the bottom, when studying sound. So the difference we said between sound and light was that the wavelength was very, very different. Light has a much shorter wavelength than sound does. So here it is represented with the wavefronts. We have the wavefronts, which were first introduced when we talked about sound as being a maximum of a traveling sinusoidal wave. So you can imagine those as being a maximum of a sine, another maximum, and so on. So the distance between two wavefronts corresponds to the wavelength. Here in the case of light, it is much smaller than it is in the case of sound. Because of this, first let's start with sound. Whenever sound comes in from the left towards the obstacle, the part in the middle is blocked by the obstacle. However, the part that goes up and down compared to it will slowly start to bend around it. There is a part in which sound cannot reach, but eventually the wave will reform itself and the sound will continue propagating. This effect becomes faster and faster the smaller the obstacle is compared to the wavelength. So if the obstacle is very, very small, the wave will almost not be perturbed by it. However, in the case of light, since its wavelength is much smaller, it is almost entirely blocked by the obstacle. In truth, if we zoomed in around this part, we could see a very small curvature, like we'll see in the case of sound, but negligible compared to the overall effect. This is also the case while some waves can get around big obstacles such as mountains, whereas others cannot. This depends on their wavelength and thus on their frequency. For instance, AM radio wave can reach more areas in general than FM because of the difference in their frequency and thus their wavelength. To explain why there is a curvature like this, we'll have to go back to a case we studied a bit more. In here, we had an obstacle inside of some kind of vacuum. The principle would be the same for the opposite, while having a slit inside of an obstacle. We'll go back to the case of a slit to gain a better understanding of why this happens. First, a short summary of what I described. So the regimes that can happen whenever the wavelength is a lot larger than the obstacle, meaning a small obstacle, the wave can go around it very easily. If the obstacle is very large, the wave is blocked, such as in the case of light and the pad. And whenever the wavelength is of the same order of magnitude as the size of the obstacle, the wave is transformed significantly. So it's not the same anymore, but eventually it can go around it given enough distance. So what we studied was interference with two very, very thin slits. In our study, we treated them as being infinitely thin, since we only fitted one single source in our analysis. And in this case, we got circular wavefronts going outwards. To illustrate better what I'm about to introduce, I'll reduce, instead of having two slits, I'll go back to a single one, just to have a view of the wavefronts created by this single, very thin slit. Not infinitely thin here, it is 200 nanometers wide, but very thin. If I increase the width of this slit, which will enable us to understand what happens whenever we have some kind of obstacle, I'll put it the maximum I can. Whenever the slit gets wider, we do not have spherical wavefronts anymore. You can see that in the middle, we have an approximately plane part, whereas on the edges, it is curved. To understand it, let's go back to when we put a source in our very thin slits. So we put in our analysis a single source in the slit, which emitted spherical wavefront going towards the screen. We'll give a name to the width of this slit. Going forward, we'll call it small a. So whenever the slit is very, very thin, we are in the case where the wavelength is much larger than the size of the slit. If we make it larger, meaning we increase a to the point where it is not really greater than the wavelength, but of the same order, maybe a bit greater, but not that much, we have some more space in which we can fit more of these sources. Here, to illustrate the case, I put in 5 sources instead of a single one. If you take each one individually, it emits spherical wavefronts. So this is the spherical wavefront emitted by this source. This is the spherical wavefront emitted by this source. This is the wavefront by this source, and so on. However, when we are looking at a medium or part of the space in which we have a wave, what we see is not the individual waves created by each and every one of the sources, but the combination of all of these waves. When we took a look at interference on the right part, we did not see only the spherical wavefront of this one and only the spherical wavefronts of this one, but the combination, the addition of the two. This is the same whenever we have a larger slit. What we see is not a bunch of individual spherical wavefront, but their combination. So all of these little circles going outward more and more combine, add up to create zones where we'll have constructive and destructive interference with wavefronts of their own. So in the middle, you can see already with the circles, it tends to be already, even if I only put 5 sources, to be approximately a plane. So we end up with planes in the middle. But on the edges, we're much closer to one of the sources. Here, the one at the top. Here, the one at the bottom. So the wavefront tends to resemble more the wave emitted by this wave. So here it tends to curve to resemble more what we will have for one of these sources. But in the middle, it is approximately as close from any of these sources. So we have the combination of all of these, which add up to create something plane on the edges, the curvature created by the added weight of one or few of these very small sources. And all of these sources, like we said, will create their own waves, which will add up. And whenever we have a screen somewhere, we will get the overall interference pattern of all of these sources combined together. So we define diffraction as being very similar to interference. In fact, it is the same phenomenon at its roots. But instead of having interference between only 2 sources, each located in their own slit, we have the interference of a bunch, in fact, a continuous distribution of sources, all jammed inside of the same slit. But at its roots, it is still interference of some waves. Here I put the intensity. I'll just go back to the animation to show it off before I discuss intensity some more. So I'll go back to a single slit. I'll give time for the pattern to form. Maybe I'll put it a bit larger. Yeah, should be fine about here. I'll give it some time to stabilize. Great. So again, what we observe on the screen is the resulting interference pattern of all the sources jammed here, which combine to give some kind of pattern on the screen. The logic is the same as when we study interference. The bright parts correspond to constructive interference, the dark parts to destructive interference. This part is very visible. However, we have some less visible but still bright spots on the edges. I'll put in a graph of the intensity to show them off. So we have, this is the intensity of the light. So again, the greater the intensity, like here it is very large, the brighter it is. We have a very bright spot in the middle, but if I zoom in, we have some others here, some satellites on its edges. So again, not only one single fringe in the middle corresponding to rays going straight from the left to the right, but some kind of pattern which is formed by the interference of all of these waves. So here the intensity is what I represented on the diagram over here. So again, this is the obstacle with some aperture in it, a slit of width A. Here is a screen. I again represented with a dashed line, the center of the system, which corresponds to the center of the slit. And I put in a graph of the intensity of the light. Again, I put the axis going towards the left, and this is the curve we get on a screen. The more we have a point to the left, it means that the intensity is greater. We have a brighter fringe on the screen, and we have some other bright fringes, but not as bright. And some places where the intensity drops to 0, we have a dark fringe. Since we do not only have 2 sources, but in reality a very large infinite number, The demonstration is a bit hard to do. If you really want to take a look at it, it is in your textbook. However, I do not. You do not have to take a look at it if you don't want to. So if for you are unsure, I'll just skip over it. The result we get from the demonstration of how all of these sources interfere together is the equation at the bottom of the slide, which has the following meaning. Theta in this relation is again the angle from which we measure at the center here to a point on the screen. And the values of theta that respect this equation correspond to the location of the minima of of intensity, meaning where we have dark fringes. So the value of theta correspond to the angle that goes over here, the angle that goes over here, the one that goes over here, and the same thing in the bottom part of the diagram. So the angle that describes this location, one that describes this location, and the one that describes this location. A is again the width of the slit, lambda the wavelength, and m is an integer. In your textbook, they use a small m. I tend to use a capital one just to distinguish it from interference. However, you can use a small m if you'd like. It doesn't change anything. It is an integer, which corresponds to the index of the minimum we're all looking at. The first one in the top half of the screen has an index of m equal +1, the other +2, the other +3. And in the bottom part, we have the first one is m-1, the other m-2, the other m-3. The value m equals 0 is not allowed because of this. From this equation, if we were to put in a value of m equal to 0 for the equation to be true, we need to look at an angle also equal to 0 for the sine function to be 0. However, looking at an angle of 0 means looking at the center of the screen, but it is not true that we have a dark fringe in the middle. In fact, we have a very, very bright one. So the value of m equals 0 is not allowed due to the presence of this bright fringe. Also, something else to take notice of, in our study of interference, we had a shift between the values of m and the number of the dark fringe we were looking at, due to the fact that the first dark fringe above the center had an index of small m equal to 0. This is not the case here. In diffraction, we do not have this shift to deal with. The first minimum above the center has an index of m equal to 1, simply. So we'll have to use this equation so far before we move on to the rest. So far, would you have some questions, something? Very good question, Catherine. Yes, we'll only ever need to locate the dark fringes. In fact, the bright ones are a bit difficult to spot. They are not even in the middle, or at least not exactly centered right in the middle of two dark fringes. What we'll sometimes be interested in is having the width of a bright fringe, but in order to find this, knowing that a bright fringe has to be located between two dark ones, if we can find the location of the dark fringes, we'll be able to find the width of a bright fringe. But we'll never have to find the location of a bright one. We need to have an expression for the intensity, which is a bit complicated to get. So we won't we won't ever need to find the location of the bright fringes. No problem. As always, do not hesitate to ask a question whenever. I'm always keeping an eye on the chat to see if something pops up. Don't hesitate anytime, just type in your question, or if it is long, type in question before continuing, so I know that the question is coming up and I have to slow down the pace. So please do not hesitate to ask anytime. So from this equation, we'll be able to find the angular position of the minima of diffraction of the dark fringes. To find not just an angular position, but a position in meters, we'll need some other equations. We'll go back to what we studied whenever we took a look at interference. We first started by doing a bit of geometry. We had defined just a random location on the screen, whether or not it is dark or bright doesn't matter at all. We defined y as the location compared to the center of the screen of this point. L, the distance between the slits and the screen. In the textbook, also, they use some different symbols for L. In the case of interference, they use capital R. In the case of diffraction, they use X. They are really the same thing. In any case, they are just the distance between the slits, or slit singular in this case, and the screen. They represent the very same thing. They use two different symbols. I'm not quite sure why, but the two of them, and again, geometry didn't break since yesterday, so we can still write tangent of this angle as y over L. And by combining these two equations together, you can find the position y of a minimum of diffraction on the screen. Also, going back on Catherine's questions, something you will have to find sometimes is the width of the very bright fringes in the middle, which we'll often call the central peak of diffraction. You will sometimes have to find the width of this fringe. So by finding the position of the dark fringe of index +1 and -1, which are at its edges, you can find the width of this particular peak. Otherwise, you just have to know which minima are on the edges of the bright fringe you want to find the width of, and then you can find its width. So we have the definitions of the symbols here. So L and Y and theta have the same meaning as we had before. A is again the width of the slit, lambda the wavelength. M, as we stated, the index of the minimum diffraction, which is an integer, positive or negative, but cannot take the value of 0, because that would represent the center of the screen, which is not dark at all. And again, if we have a small angle, meaning we're not looking too far away from the center, it is often the case whenever we are looking at the first minimum of diffraction. If you're looking beyond the first, it might not be as great. But if you're looking around this location, we can use again the small angle approximation. In that case, we had that the sine was approximately equal to the tangent, since both were about equal to their angle in both cases. The tangent can be written as y over L. The sine, since we had a sine was equal to m lambda, the sine is equal to m lambda over a. And then we can isolate y, in this case, to get an expression when we have a small angle of the dark fringes in the case of diffraction, with the index of the dark fringe we are looking at, the wavelength we are sending, the distance between the slit and screen, and the width of the screen. Also, we can get some intuition from this. So again, just like in the case of interference, whenever we increase lambda or L, y we increase, meaning the dark fringes and by extension, the bright ones too will go more towards the outside, and A, the width of the slit. Whenever this increases, Y, the position of the satellites, will, whenever this increases, this will decrease, meaning you will get more towards the center. We can take a quick look at it. If I have, I'll start it at a grade value. So here we have the satellites over here. We have a value of the width of the slit here of 1,200 nanometers. I'll decrease this, meaning I decrease A. Take a look at what happens with these. Okay, maybe that was a bit much. Seconds, I lost them. They're really easy to lose. At some point, they come closer to the middle, so at some point they become drowned in the central peak of diffraction. I'll try to make them reappear by slowly increasing A. They really get lost. Okay. I'll have something better next week. I have some other software I'll be able to show you with, but in the meantime, sorry. But still, last thing we can say about this with this expression, we can also see what happens in everyday life. You generally do not encounter a very thin obstacle or slit. You instead deal with much larger ones, which are sometimes called windows. So a window is a very large slit by itself, and if the width of the slit is very large compared to the wavelength, such as is the case whenever you're looking through the window, Y becomes very, very small. So all of the satellites, all of the bright fringes and dark fringes outside of the central peak of diffraction are all brought together near the center and become indistinguishable. So at our scale, unfortunately, we cannot see diffraction due to this. We have to work with very small slits, which can then project a pattern on the screen and we can see it visually. But with slits and obstacle our side, it is not something we can see with light. We can hear it with sound since it can get around objects, but not see it with light, unfortunately. And with this, that will bring us to the end of the theory for today. So with these last equations and theory, you'd be ready to take a look at some more examples. First, example 36.1 in your textbook, and also two more exercises I put on there for chapter 36. So again, you can take a look at them. They have the same remarks I would have done in the class under normal circumstances. Also, in the add-on to the study guide I published a few minutes ago, just before the class, you have about 4 more exercises to do based on this. So if you have some more questions, please ask them now. In the meantime, what you can expect from next week. This week, we studied first the interference created by two very thin slits, first on its own. Then we studied the diffraction due to the interference of the wave created by all of the sources inside of a single slit. But in reality, whenever we have two slits, each of them has a finite width. So the real pattern we see whenever we project something on a string with interference is the combination of the two. We have two slits, each with its own width, so each having the effect of diffraction, interfering together. So we'll have the combination of the two to work with on Monday. And then we'll also move on to diffraction gratings. which will be systems in which we have more than two slits. It can be 3, 5, 10, a million. We'll learn to study these cases, more precisely those in which we have a very large number of slits. It might seem counterintuitive, but these kind of systems are very much easier to work with whenever we have a large number of slits. So we learn to study them. This is a case that is useful, especially whenever we want to do spectroscopy. So we want to study elements based on their emission spectrum. And for this, we have to distinguish all the colors that are being sent to us. So diffraction grading will be a system that will be able to separate all these colors and enable us to analyze them. So, well, that would be all for today's rambling. So, last time for questions before I end today's class. Otherwise, do not forget to answer me through mail whether you would like us to continue having classes for next week. So I'll be available to answer your questions. If you prefer us to have it at 1 or 5, depending on how your schedule is organized, please don't forget to confirm with me. So otherwise, thank you for being today, and I'll see you on Monday.